So looking at the x squared minus divided by 3 minus 4 equals 8. So this was the strategy that Nathan first employed, and DJ, I believe you did this one at first as well, right? Huh? Say again? I will say this, I thought you tried to do it, but you just multiplied here by 3 and here by 3, forgetting the 4. Do you remember that now? Yeah. So, please notice, if you multiply the right-hand side by, or the left-hand side by 3, okay, so first off, Grayson, why did Nathan and DJ multiply by 3 here?
To get rid of 3 from the x.
Okay, so why would this multiplication get rid of this 3?
To get the x by itself.
Yes, but like, why does that get x by itself? Why does that get closer? Okay, how did they know to multiply that?
Because division is the inverse.
That's what I was looking for, right? We have to recognize that there is division, and the inverse of that division is multiplication. At its core, if you're writing this out, right, you would want to show the distribution. And then 3 divided by 3 is 1. We all go with that? Okay. So x squared minus 12 was equal to 24. And then what step? And so like that would have been step 1 probably in the calculator, depending on how you worked it out. So from here, what could you do?
Add a plus 4 on both sides.
Yes, but is that what we would do for this strategy that Nathan employed? Plus 12. So, for those of us who didn't use this strategy,
I was all the way at the top.
for those of us who didn't use this strategy, does this look familiar? X squared is equal to 36? Yes. So is there more than one way to solve it? Yes. For the rest of us who, I will say this, the other way is how I usually would solve it. If you remember, I talked about this before. The last operation being done is the first one that I like to undo. So what's the first thing happening to x? It's being squared. After it's being squared, what's happening? Being divided by 3. And then what's happening? Subtracting by 4. The last thing being done is what I like to undo first. It's easier, so you don't have to worry about the distribution, things like that. So I could have added 4 here, is what a lot of us did. And that's what Gracie was talking about. And then times 3.
That's 12.
Thank you. I just misread it. That's what happens when you move too quickly, right? So x squared is equal to 36. There we go. And so from here, I think most of us are getting better at this. What are we going to do at this point? Take a square root, right? The inverse of that square is a square root. Don't forget, the whole point is that the square root and the square cancel out. Technically, if you remember so far, we've always created zeros or ones. What we're doing is we're making a 1 for the exponent. So it is still creating a 0 or 1, it's just on the exponent. And so x is equal to what? 6. Anything else? Or negative 6. And so I actually figured out a way to type that into the calculator. I'll show you that in a second. We all good on this one so far, though? Yes? Ready to move forward? Yeah. KJ's like, no, Mr. Kenny, I don't want to do math. Stop making me. What's the next equation that we had? It was 2 times x plus what again? 3.
Raised or squared.
Raised to the second is equal to 8. So, how many of us wanted to distribute that 2 first? Because we're just used to distributing. Can we just distribute here? Why not? Well, there's a square there, right? Remember that square comes before multiplication. But I can't really square it. Like I could, and I do want y'all to notice this. If I were to take the time to square it, I would get 2 times x squared plus 6x plus 9. Let me make sure we all understand that, where that's coming from. To square it, what does that really mean?
2 times.
Multiply by itself, right? And so what would I have to do now to do x plus 3 times x plus 3? Distribute, right? When you distribute and you simplify, that's when you get this, okay? But then, do we know how to solve this equation? Have we ever solved an equation where there's two variables, or the x squared and x is there?
Yeah, standard form.
That is standard form, but what I asked is, have we solved it like that? No. We've written standard form, we've worked with standard form, we know certain things about this, but no, we've never solved it like this. So we don't want to distribute. And you also, so you have to do the square first and then distribute, but that doesn't make our life easy. So what can I do with this equation? Divide by 2, right? Use your inverses. Use those inverses. 2 divided by 2 is 1. Then I'm left with x plus 3 squared is equal to 4. Next step. Now I can take a square root, right? Again, the whole point is using those inverses. X plus 3 is equal to 2.
Wait,
Is it just 2?
negative.
So notice this is where we would want to do plus or minus 2. Okay? You don't just magically make it plus or minus at the end. It's that 2, there's that 4 that could have been a positive or negative 2. So when I subtract 3, what is 2 minus 3? Negative 1. And what's negative 2 minus 3? There we go. We good on that? Does that help us? LaShannon, do you feel a little bit better about it now? Yes? Anybody want to ask any questions about that before we move forward with today? We're going to look at the equation, or the graph in a second.
Okay, so when it's just, it's like two different equations. When it's one square root and you don't have to add or subtract a number after you get a square root, it's the same number but positive and negative.
Right, because, and so like notice that's what we had right here, positive or negative. Right, it's when you take the square root that you get a positive or negative. Because we had nothing else going on here, right, when I took the square root I got positive and negative 6. But because I then had to subtract 3, I had to do a positive 2 minus 3, and I had to do a negative 2 minus 3. It's when you take the square root that you get a positive or negative. Does that help clarify that detail? Okay. So yeah, it's when you take that square root that you're going to get that positive and that negative. So let's look at the graph quickly. All right. And I'll turn the lights off so that we can see the board a little bit more easily. 2 quick things, just so you can see this. I found out afterwards, if you want to type 2 solutions in, what you can do is you can do x equals negative 1 and it'll let you put that and in there. X equals negative 5. So if you have 2 solutions, that's what you'll need to do on the calculators. Make sense? We good? Just be aware of that. So 1.3. What's the first thing you have to do in order to get the equation for this function? Before you even get the y-intercept. You can make a table to get the rate of change. Say again, Jada? Identify the function, right? Which that may be a step that we're already doing in our heads without consciously thinking about it, but you have to identify the function, which if you look at the graph, you might realize it's what? It's exponential, right? But Shannon, what else can you make to figure out that it's exponential? A table. And so this is what Lexi was eventually getting to. You said make a table, right? Or you said rate of change. Shannon said table. So what's a point that we should put on this table? 0, 3,
6, 1, 6,
1, 6,
2, 12,
and 2, 12. And from this table, we very quickly see 2 major things. What was the first thing you said, Lexi? Before you said rate of change, you said something else. Does anybody else remember? If we're writing the equation, okay.
It's multiplying, you know what it is.
Right, it's multiplying by 2. So if it's repeated multiplication, is it the exponential we thought? Yes. And where I would start next is, what is the general equation of an exponential function? Okay. So what is this A? 3. That's my y-intercept. What's that B? 2, that's my common ratio raised to the x. Okay? I need you to notice, it's hard to write these equations if you don't know those equations. Like if you don't know y equals a times b to the x, you're going to be in a rough spot, right? Do notice, and don't forget, because we've gotten away from it for a little while, it was our last understanding check, or 2 understanding checks ago. But you need to be able to identify functions as a part of this unit that will be on the unit test next week. So make sure you look back over that understanding check before the test. Any questions? Ready to move forward? Yeah, Mr. Kennedy, we're doing great. Bet. All right, cool. Moving on. Unless anybody has any questions, real talk. Going once, going twice. Sold. Don't forget, if you haven't already turned in M177, if you can get it to me by the end of the day, I won't count it late. I should have your graphic organizers and your understanding checks back to you tomorrow. I don't know if I told you all this. I haven't taught geometry in about 7 years. Is that M1-77? Okay, I'll come and get it. But I haven't taught geometry in about 7 years. It is really hard to teach a new class. It takes a lot of time, like planning activities that students can learn from. So I apologize for not getting things back quicker. I usually have a 1 day, max 2 day turnaround. Yeah, that hasn't happened this year, and I'm sorry. But I'll have those back to you tomorrow. Here's what we're looking at. Lesson 5, the root of the problem. This is from the textbook, so we definitely need our textbook out. We're going to continue with what we were working on yesterday with these objectives. So remember, I told you that there are ways to algebraically solve each of these equations, even in standard form. And I'll go ahead and tell you, I know that the other Algebra 2 teacher taught that. It's called factoring, not factored form, but algebraically factoring. But in the 21st century, we have graphing calculators. No sense in making it harder than it has to be. So let's look at a couple of details about how we can graph this. Did we finish all 4 of these yesterday, or did we have one left? We finished we finished going over D as well?
No.
I didn't think we finished going over D. I think y'all worked on it within your small groups, but we didn't quite go over it. So let's look at D together. So let's start here. Jaden, what is a step I could take to solve this equation? No, so I'm not saying the best one or the first one. I'm just saying what is a step I can take? If I add 18, why would that be beneficial?
Get rid of it. How
does that get rid of it? When you say that, what do we mean?
It's the inverse.
So it's creating
operation.
a
Zero.
0, right? We want to recognize we're creating a 0 there. Would anybody have done anything different, or do we like that method? You like that one? Yes, LaShawn.
I would do my 2 I would multiply my 2 places.
You would have multiplied what?
My 2.
The 2, so like multiplied by 2 here.
Yeah.
Just make sure when you do that, you distribute it to both sides. Totally valid, right? That also works. Remember the way I like to think about it is whatever the last operation is, that's the first one I'm going to undo. So what's happening to x? We're adding 5. After we add 5, we're squaring it. After we square it, we're multiplying by 1/2. After we multiply by 1/2, we subtract 18. Right, and so I go through that process of identifying what's happening to the x, and that's how I figured it out. But multiplying by 2 is the inverse. As long as you distribute properly, you're good. Okay? So 1/2 times x plus 5 squared is equal to 18. Now what would we do, LaShannon, for sure?
You gotta do it with 2.
So I'm going to multiply by 2. Right? And I will point this out. I know y'all thought I was crazy, but this is a big reason why I ask students not to say 1/2. When you train yourself to think about this as 1 divided by 2, you very quickly recognize the inverse of division is multiplication, right? That's why I want you thinking about it as 1 divided by 2. It helps you long term. So x plus 5 squared is equal to 36. DJ, what am I doing next?
The square root.
Taking square root. So KJ, what is x plus 5 equal to? Right, first off, that obviously is canceling. That's the whole point. What is x plus 5 going to equal?
6.
6?
Or negative 6.
or negative 6, right? We want both of those. Fantastic catch. All right, last step.
Oh, subtract 5 from both sides.
There you go, right? So minus 5, that creates a 0.
Positive
So positive 1.
What did he negative 1
1. 1 or
Negative and
Say it again.
negative.
Negative 11.
Yeah, 11.
Because remember, it's a what is 6 minus 5?
Oh, yeah.
1. What is negative 6 minus 5?
Oh, so it's always gonna be 2?
Because remember, it's what it really is, and that was a great catch by Jaden, x plus 5, remember, is equal to 6, and x plus 5 is equal to negative 6. Right? So you have to think about it as positive 6 minus 5 and negative 6 minus 5. Does that make sense? We good on that?
I didn't get C.
You didn't get C either?
No.
I'll go ahead and just tell you the answer for that one so you can check it later if you need to or want to work through it.
Can I?
Plus or minus 4, 1, so 5
It's x equals 3.
and negative 3 are the solutions there. We just need to get to the next part of today. And I will say D, is it safe to say that's much harder than C is? A lot more going on there.
Yeah, that's not hard.
Say again.
It's a lot more going on.
A lot more going on. And it's not, I would say that, it's not harder, but there's more going on. So if you can do D, if you're comfortable with D, you should be able to do C. Alright. So here's the next part of it. Alright. This is where algebraically, hopefully in Algebra 1, you heard about a term called factoring. I'm going out on a limb and saying some of us did not, because I know that some of us had a rough time with our Algebra 1 teacher. So instead of factoring, what should factoring make you think about?
I don't know.
Factoring should make us think about what? Factored form, right?
Oh.
So instead of making our life hard and learning how to algebraically factor, we're going to use our graphs to factor it, right? So, two quick things. In this problem, we have x squared minus 4x is equal to negative 3. You can factor it there. However, as you will notice here, they added 3. Why would they add 3?
I don't know.
To get rid of the 3 on that side.
To get rid of the minus 3 on this side, creating a what?
0.
Hey, quick question. What's another word for x-intercepts?
Root.
Zeros or roots. So what do we typically want? A 0. On top of that, and so I want to point this out before we get too far into this, x minus 3 times x minus 1 is equal to 0. The reason why we also really want to equal to 0 is because of this thing over here. Notice this detail. The zero product property. What is anything times 0? 0. So, for this to equal 0, either x minus 3 has to equal what? 0. Or x minus 1 has to equal what?
0.
Does that work if we have something other than 0 on the right-hand side? No. So please make sure you make a note of this. To use factored form,
So you gotta make a 0.
right, to use factored form, one side of the equation has to equal 0. So you can use this, right? To use factored form, one side of that equation has to equal 0, so you can use that zero product property, right? And it's just that idea that if we're equal to 0, at least one of those factors had to equal 0. So either x minus 3 equals 0 or x minus 1 is equal to 0. Yes, ma'am. Jada.
How did they get x minus, where is that coming from?
The x minus 3 times x minus 1? So,
It's confusing.
hold on. So remember, I haven't gotten into that part yet. Don't stress about that, okay? My only point up to this point is that we have to have it equal to 0 so that we can use the zero product property. They're using an algebraic process known as factoring. But does anyone recognize this as a form of the equation that we've studied?
Yeah.
What is it called? Say that one more time. Factored form. Remember we just said it. Factoring should make us think of factored form. So let's stop here. We don't know how to algebraically factor this, but does anybody know how to find, hey, what are the things in the factored form called? X-intercepts or zeros or roots, right? X-intercepts, zeros, or roots. Does anybody know of a strategy that we could use to get the roots or the x-intercepts for this equation? What do you mean by solve it? Okay, but how are we going to solve that?
We could plug in our like once you get it in the right factor form, then you can figure out what each one is.
Right. So, and that's what I want us to understand. What we're trying to get to is the factored form. X minus, or A times what? X minus.
X is second plus B.
It's already factored form, or standard form.
Sorry.
X minus what? R1
1
times.
x minus r1.
So where can I find R1 and R2?
The one right there in the corner.
So I'm hearing a couple things. KJ, first I want to point out, if I had the roots in this equation, then I wouldn't need this equation, right? But what's another word for roots? Zeros or x-intercepts. So Lexi, where did you say we could find those roots?
A graph.
Can we graph this equation to find our roots?
Yeah.
Okay, so and please make this note to yourself, to get the factored form, we're going to graph it and find our roots that way. To get factored form, we're going to graph it and get our roots that way.
So we don't have to do it algebra.
Exactly.
Okay.
Okay, so,
Oh, shoot.
CD, you're usually over there. Jump into group 4, we move groups around since LaShannon was on her own. Can I erase this written part up here? Okay. So, what was the equation?
X squared minus 4x equals -3.
So that's what we started with, but remember, we had to be equal to 0, so I need the left-hand side of that.
X squared minus 4x plus 3.
So we should all be typing this in, x squared minus 4x plus 3. So there's a graph.
Are those the x-intercepts?
Say again. Where do you think we see our x-intercepts? So remember, the graph that you need to put in, you need to put in what's on the left-hand side that is equal to 0. Because again, what are those roots also called?
Zeros.
X-intercepts or zeros, right? So we need to be equal to 0. So does anyone see my x-intercepts?
Oh, it's 1 and 3.
Okay, is it just 1?
0, 1, 0, 0.
Or was it 0, 1 or 1, 0?
1, 0.
1, 0. Remember the y value is 0, this one is
3,
3, 0. Okay? So now, first off, what is my a value for that factored form? Ooh. Hey, what's my a for the standard form?
Yes. 1. Oh.
A x squared plus bx plus c. So a is understood to be 1. So what's my a for the factored form? 1. Right? So 1 times x minus 1 times
X minus 3.
is equal to
0.
0. Hey, do you think all x-intercepts are going to be really nice and pretty like 1 and 3? No, so it'd be really nice if there was a method in the calculator that could tell us exactly what the x-intercepts are, right?
Yeah.
Anybody have an idea?
Menu.
Okay, let's hit menu, right? So once we hit menu, where are we gonna go?
View. Wait.
Does anybody remember how we found the vertex? What we went to? Didn't we analyze that graph? Because we analyzed it and found our maximum or minimum. Let's go to analyze graph. Anybody see an option? So remember, minimum or maximum was for our vertex, right? Are we trying to find a vertex right now?
So zero.
We're trying to find zeros, right? Because what's another word for x-intercepts? Zeros. So find your zeros. Notice how it's giving you that dashed line again, lower bound and upper bound. Please pay attention to this. You can only find one x-intercept at a time. So my lower bound needs to be below that first x-intercept. Notice I went just to the left of that one. And I saw a lot of people just going way to the right-hand side of that vertex. But here, if I go too far, aren't I going to get both x-intercepts in that thing? The calculator will freak out, doesn't know which one to do. When it says upper bound, just go a little bit to the right until you see that x-intercept pop up. So are we correct? 1, 0? So I'll go through it again for the 3, 0. Remember, we're going to go to analyze graph, 0. You see how I asked the question in the bottom left-hand corner, lower bound. So that means I need to be to the left or to the right of the x-intercept? To the left, right, lower to the left. So I'm a little bit below or to the left of that x-intercept, 3.
Are you gonna be putting it like on the point?
Well, so notice, when it was lower bound, I hit enter, and it's going to leave a dashed line right there. So notice if I scroll to the right, you see how it has that shaded region? But it's asking for an upper bound now. Lower bound was to the left, upper bound is to the right. So make sure you go to the right. And if you go far enough to the right, what do you see right here? The other 0, the other x-intercept, right? So once you get that other x-intercept, you're good. You hit enter again, and there it pops up.
3, 0.
Say again?
The 3, 0.
3, 0, yeah. Which isn't that what we said it was going to be? Yeah? Jada, do you feel less stressed out about getting that factored form now? Right? So that's why I taught you those different forms, because then it's pretty straightforward from there. So now we have this equation, and we already talked about it earlier. What can I use when I'm set equal to 0? The 0 product property. So that means x minus 1 is equal to what? 0. And x minus 3 is equal to what? So what do I do to solve for x?
I thought we did it. So we saw the equation.
So x is equal to, oh, isn't that the first root we just found?
Oh, yeah.
X is equal to 3. Wasn't that the second root we just found?
Yeah. I'm confused on what's the answer or something.
Well, remember, we're trying to solve this equation.
Yeah,
So we want what makes this equation,
true.
so what makes this equation true?
X. Wait, so, okay, that's the answer. Okay, see, that's what I was talking about. I thought this was an answer.
Right? So remember, we're trying to get the factored form, because then we can set each factor equal to 0 and then solve for x. So both 1 and 3 will make that equation. Yes?
So if we graph it, do we have to do that part?
That's a great question. No and yes. Here's what I mean by that. I say no because will you get the 1 and the 3 right from the graph?
Yes.
100%.
What you want to show.
Your future math teachers will expect you to get this factored form. And then set equal to 0 and solve. Is it necessary? No. But I need you to practice doing that because future teachers will expect that out of you. Realistically, they'll even expect you to go through the algebraic work of factoring. But if you can graph that and get your roots, you don't have to go through the work of factoring it. Okay? But I guarantee you they will want to see the factored expression. That's why I'm asking you to write out the factored expression. KJ, you look like you don't like that. Why not?
I was saying like who? You said teachers are gonna expect you to do that.
Well, I mean, if you're in here and you're taking pre-cal next year, because you're a junior, you have to do that for sure. And a lot of colleges will expect you to get the factored form if you take a math in college. Like, there'll be times when you're just getting the factored form and not even solving for x. So that's why you need to be aware of that factored form and how to get those roots. Okay?
So which one do you think, do we have to use this method,
Use what?
the graphing method? Or can we use the algebra?
You can use the algebraic method, but do you know how to algebraically factor?
What you mean, like what we just did? Or,
No.
is that
So-
what we just?
We factored based on the graph. To algebraically factor, what you do is you pay attention to this number, and okay, factors of 3 that would add up to be -4, that's -3 and -1. So then you split up that middle term.
Never mind.
You're not a fan of that?
Erase.
Minus 1x plus 3 is equal to 0.
It's not, it's fine.
And then you look at these two things, you're like, oh, they both have an x in common.
Erase.
So I factor out my x. These don't really have anything in common but a -1, so I factor out the -1. And I will point out, this should look like after we have distributed. So what we had before we distributed was x minus 1 times x minus 3. Right? That's factored. That's exactly what we've got, but isn't it easier to just find the roots on the graph?
Yeah.
That's why I taught you that way. It's a good question, and I do want you to see, like, you can do it.
No.
I can't.
Huh? There's just no need to make it more complicated than it is. Is that safe to say? Okay. So that's why I'm approaching it this way. Let me see if there's any other notes that I made to myself. Yep, nope, that's it. I did have a note here, so I do want to go ahead and tell you, you cannot always factor because of the type of roots that you get. But I will point this out. Does anyone recognize what form we might consider each of these equations in? Would they be close to? A vertex form. You see how it's x minus h squared? Do you think it will ever be the case where we can't solve it in vertex form?
Yep. Yeah.
No.
Really?
That's the beauty of vertex form, is that you can always use vertex form to solve an equation. Factored form is it's not always that true. And I'll show you a couple of cases.
Don't you solve the same way though for both?
Well, so let me point, so what I mean by that, so let me go ahead and show you this. Before we get too far, because that is a great question. So let's change this to a +7. Can I still get the vertex from this graph?
No.
I can't get the vertex?
What?
Yeah.
Yeah, and remember, we can analyze the graph with the calculator. There's my vertex. So can I get the vertex form
Yes.
and solve it? Yes. Can I get a factored form?
No,
No.
Why not?
because they're not going through the x-axis.
I don't have, it's not going through the x-axis, so I can't get x-intercepts, so I can't do the factored form. That's why I say we can't always use factored form, but you can always use vertex form. So that's something I do want you noticing. So can you solve a quadratic equation using vertex form every single time?
Yes.
Yes. Okay? Factored form is just one of those things that you want to be aware of because other teachers will expect you to know how to do it. Okay? So let's look here. Let's get some practice with this. So use factoring to solve each quadratic equation if possible. Think we can work on this within our small groups? Get some practice on our own. And so don't forget, can you go back to your notes on the previous problem?
Yes.
Yes. Can you talk with your small group?
Yes.
Yes. Should you talk with your small group?
Yes.
Yes, right? When you talk with your small group, you will learn more than me just telling you what to do. That's why I have you working in small groups. All right, let's go ahead and get to work. Let's try to wrap this up in about 20 minutes, and we'll look at it from there. What are you saying? Yes.